This is going to be a dramatic departure from what you've seen this morning, or all day rather. You've seen all these high-tech solutions and beautiful applications, but now we're going to go old school. I've got a few things I'm going to show you using some simple indicator methods to do a couple of different tasks. Some of the things we're going to cover today then are using this indicator method to quantify the continuous mineralization in drill holes using simple binary indicator methods. I'm going to show methods that you can use to calculate dilution and ore loss using composites. And then I'm going to show how you can use an indicator method to define mineralized continuity for classifying resources. And then finally, a couple goofy little things that I've come up with for modifying resource classification. So we'll kick it off here with this continuous, or this concept of continuous mineralized lengths. So the first thing that we do is in our drill hole file, we set an indicator flag with a 0 or a 1, depending upon whether that assay interval is above some cutoff grade. Then we need to create a separate composite file for each cutoff grade that we want to look at. Then we go ahead and generate composites for each of those cutoff grades, and we're going to use those 0, 1 indicator flags as if they are a geologic item. What I do is I set my composite maximum length to something that's longer than my longest drill hole, and then those 0s and 1s are going to control the compositing. After I've got each one of these composite files constructed, each one represents a different cutoff grade, there are a variety of ways then to assemble the statistics, and we'll look at that. So, as I mentioned, we need this grade indicator flag item. You set it up with a min of 0 and a max of 1 with a precision of 1. We need a composite file and its associated file 12. I don't know how this is going to work with torque. I'm sure it will work fine. So we need a pair of file 9, file 12, or this is my practice for each cutoff. So I use multi-runs for all of my model builds. This just shows a panel where the last two procedures here are the second to the last procedure sets these indicator values to 0 for all intervals, and then the last one goes through and sets a 1 if the drill hole assay interval is above a cutoff grade. So here's just another panel for from the multi-run to do that. So this panel shows multi-runs where I'm building the composites, and if you haven't used this vary file function, it's really handy when you've got multiple, say, file 11s or file 9s. It's a real handy way to just process through your data. So this is just a quick illustration, and for all of my slides here where you see these drill holes, we're going to assume that the file 11 or our assay intervals are 1 meter in length. So in this little illustration, we've got 2 intervals that are above a cutoff grade on the left side there, the file 11. And so when we create our composite, because we're using 0s and 1s as geologic items to control the compositor, our composite now ends up, we've got 1 2-meter length of continuous mineralization above a cutoff grade. In this example, our final file 9 ends up with 2 mineralized lengths. One of them is the same length as the original raw assay, and then we've got a second one that's combined. It's a 2-meter long length. And finally, here's one where we had 5 contiguous mineralized intervals in a drill hole above cutoff, resulting in this case a 5-meter long interval above cutoff. So once these composite files are created, there's a variety of ways to assemble the statistics. You could use MSDA. You could export the composite data out to Excel, or you could write a script to calculate the stats. And that's what I do. Like I said, I'm old school. I'm still using awk, not Python. But my program will output something similar to this. The key information here is down the left, or the leftmost column. It shows the length range, and I'm counting how many there are, tallying up how many meters there are, calculating the average grade, and getting some cumulative stats. So we can go ahead and graph that data from the chart, and we see that in this case, in this deposit, we've got a lot of our continuous mineralized length in the range of about 1.5 meters or so. So if we put a cumulative curve to that, we see that 50% of our mineralized data are in the range of 0 to 1.6 meters in length. So that's telling us something, that we've got thin mineralization, and dilution may be a real issue. If we just look at this cumulative length for 3 different cutoff grades, we can see that at a lower cutoff grade, 0.1 grams in this case, 50% of our half-gram mineralization, 0.1 gram mineralization is up to 5 meters in continuous mineralized lengths. And at a higher cutoff grade, 0.9 grams, half of our mineralization is in the order of 1.5 meters. So you can see the distribution of these grades. So with that quick little introduction, I want to go to something that's much more meaningful, and that's trying to assess the amount of dilution that you may incur by mining larger and larger bench heights or SMUs. So I'm defining dilution as the percentage of material below a cutoff grade, and that could be the amount of waste in an ore block, or the way I'm going to be using it here, the amount of waste meterage in a given composite. And ore loss I'm defining as the amount of contained metal that will be lost when that composite drops below a cutoff due to ever-increasing dilution. So here's a little illustration where we've got a drill hole, we've got the length down the left side, and a gold grade down the right side. So at a half-gram cutoff, we have a grade thickness product for this little segment of drill hole of 1.5 grams per ton meter. If we were to now create a 5-meter long composite, we have an average grade for that 5 meters of 0.45 grams. So at that half-gram cutoff, our composite now has fallen below our cutoff grade of a half gram. So that 1.5 gram per ton meter is now lost. We can't mine that. So let's just look at some of the ways to go about this real quick. We set those same 0, 1 indicators in our assay file, and then we calculate a grade thickness product, multiplying grade times the length of that assay interval, and store it. Now we create separate composite files, but instead of for a cutoff grade, each composite file is going to represent a unique length. We go ahead and build fixed length composites then, and we're going to composite the grade, that indicator field, and then that grade thickness product. And then we go ahead and assemble the statistics from each of those composite files. So here's a little illustration showing a drill hole with, in this case, we've got our 0, 1 binary indicators down the left side and gold grades down the right side. So in this little segment of drill hole, we've got two intervals that are above a half gram. So when we create a 5 meter long composite, those zeros and ones become 0.4 and the grades become 0.75. So what that's telling us that at a half gram cutoff, this 5 meter composite, 3 meters out of 5 are below cutoff, resulting in 60% internal dilution for that composite. Only 40% of our composite is above that critical cutoff. So again, pretty simple stuff. We just need an indicator that we can go ahead and set to a 0 and 1. We need a grade thickness item in file 11. And then we go ahead and set the indicators based on a cutoff grade. So typically I would be looking at anywhere from 5 to 7 cutoff grades. So I have to have that many indicator fields and that many grade thickness fields. So again, we calculate the grade thickness product here. So we also need indicator fields in our composite file, but we need to make sure that we have a precision of at least 0.01 to track the percentage from 0 to 100%. Again, we need a grade thickness item in that composite file, and you composite the grade, the indicators, and the grade thickness products. And then what we need to do is put on our accountant's hat and do a bunch of tallying of, we need the meters above cutoff grade, meters below cutoff grade, we need grade thickness above cutoff, and grade thickness below cutoff. So now that we have a tally of all those fractional components in our composite files, we can now calculate percent dilution. And it's a simple little equation where the percent dilution is simply the waste length divided by the total length times 100. And we also we tally up our ore loss. It's real simple. It's just simply the grade thickness of our ore divided by the total grade thickness of all of our data. And the little awk script kicks out a table of data. I've got, in this case, I've got composite lengths ranging from 2.5 meters all the way up to 20 meters. And what we see is that at a 2.5 meter length, we've got nearly 19,000 meters of data above, in this case, 0.65 grams per ton. And as those composite lengths start increasing, you can see that the amount of meterage above cutoff increases, but the gold grade in this case starts decreasing. Likewise, our grade thickness product decreases, and you can see that our dilution goes from about 27% up to 65%, and the ore loss from around 3% to 6%. So we can graph that. I'm showing in yellow dilution on the left side versus composite length on the x-axis, and there's a 0.85 gram in red and then the 0.65 gram in yellow. Now what I've found doing these sorts of analyses is that most often you'll incur the greatest percentage of dilution going from your raw samples to that first composite length. And as the composites continue to get longer and longer, that rate of dilution starts flattening off. Metal loss is not as abrupt, I guess, as the dilution itself, but here you can see the relationship of two different cutoff grades that, as you would expect, at a higher cutoff grade, we're going to incur much more ore loss with longer and longer composites. And ditto with our grade thickness or contained metal, if you will, we get the same sort of a relationship. So I typically will go through these sorts of analyses prior to building a model, if I'm working with mining engineers, we discuss what might be a likely SMU, what kind of equipment might be used. And so this composite link study gives us some sort of inkling as to how much internal dilution that we're carrying and how much dilution we've got in our final block model. And in some cases, the amount of that internal dilution may be so well accounted for just by compositing that the mine planners will use maybe nominal dilution for their mine plans. The last couple of topics here are a little bit, well, this one is fine here. This is a good one here, but the last one is kind of out there. But in classifying mineral resources, most jurisdictions use mineralized continuity as sort of the key thing to be looking at to classify a resource. And so one of the easiest ways that I've found to demonstrate mineralized continuity is simply to build an indicator model at some economic cutoff grade, or the cutoff grade that is going to be used to tabulate mineral resources. Then what I do is, after I've constructed that indicator model, is I'll walk through it in section and plan and look at that probability cloud to find, is there some probability where the deposit is really starting to show good continuity. And as a rule of thumb, I would require a probability level of at least 50% before I would feel comfortable in saying this is really demonstrating mineralized continuity. And then I use that estimate of probability as a guide to actually draw shapes then that would be used to code the model. I'm not going to get into the indicator estimation very much, other than to say that here's a little illustration of a block surrounded by 4 drill holes in 3D space. And I've set the 0-1 indicator on the composites based upon an economic cutoff grade. And I've chosen, or I've only allowed 2 drill hole composites per drill hole to be allowed to estimate the indicator for a block. So in this case, we've got 8 total composites being used from 4 drill holes to interpolate a probability into the block. And in this case, 4 out of the 8 are above that cutoff. So if they were equidistant from that block, the final estimated probability would be 0.5, or there's a 50% probability that this block is going to be above cutoff grade. So this is just a plan view then of a block model showing that estimated probability in, 10% probability increments, with the warmer colors being much more probable that that block is above cutoff grade. So what I do is I go in there and manually draw a shape around the blocks that I feel are demonstrating mineralized continuity. And I would usually have my drill holes displayed. If there are key geologic features like faults or some favorable lithologic unit, I'd have those in the viewer. And I draw these shapes, and typically what I would do is maybe draw one of these shapes on every 5th bench, and then quickly link them together as a solid and code a resource category field in the block model, and basically say all these blocks inside of there are indicated based upon demonstrated mineralized continuity. So this last one is, or I've got a couple kind of goofy ones here. I'm going to show you one that I have used to basically reassign a resource category, an isolated block, let's say an inferred block setting in a sea of indicated. And many times we you see models that are classified using really prescriptive type information, like how many drill holes were used, how many composites were used, what is either the closest distance or the distance to the closest composite used, or the average distance. These sorts of rules typically end up with a model that we call the spotted dog effect, where you've got these goofy patches of various classified information, and you know that that's not the way it would be in the real world. It just happens that you happen to have drilled a hole there, and that's not necessarily demonstrating mineralized continuity in by itself. So this is sort of there's a product out there was about 10 or 15 years ago called dilate and erode, where in some cases you're going to take away, erode, and in other cases you're going to dilate or add to. And the last trick, or not trick, but nearest neighbor thing is using, say, underground workings to classify resources adjacent to them. So this modification of an initial classification code works like this. What I do is I export out all my measured, if I have any, and indicated blocks. Those block centroids are loaded into a drill hole composite file, and then they're used to interpolate just a dummy grade into only, in this case, inferred blocks. Only the inferred blocks are going to be estimated with basically measured and or indicated block points. So then a user calculation can be run to reassign that preliminary resource category to another classification. So in this goofy little illustration here, we've got a lone inferred block in the center. We see the centroid locations of each block as black dots. So in this case, all these surrounding blocks would be in a composite file with their location as those black dot, or indicated by the black dot. So I cleverly set up a search strategy so that the block that's going to be estimated can see each adjacent block, not only the full side blocks, but I've got a search ellipse that will allow the corner blocks to also be eligible. So in this case, we've got 8 surrounding blocks here. And let me back up here. So the purpose here is to count how many of these blocks, if you will, were used in the estimate. And you can simply do that by saying I want to store how many composites or how many drill holes were used. With that number stored in the block, you can run a user calc then and say that if my inferred block is surrounded by, let's say, 6 blocks that are indicated, I think that maybe we should reclassify that inferred block to an indicated category. It's surrounded by a sea of higher confidence blocks, so why is that one sitting there all by its lonesome? And so the last one here, I've used it on a couple of projects that have had historic underground production. I had stoped wireframes, and instead of just using some exploration drill hole data to try to classify blocks above or below the stope in the plane of, say, a vein, I take that underground stoped wireframe and grid it to get points off of that surface, load them into a drill hole composite file, and then use them to interpolate a value into the blocks for the sole purpose of capturing the distance to the stope that could be then used in a resource classification strategy. For example, if a block is within 15 meters of an existing stope, maybe it'll be classified as indicated. So I guess I've already covered those points, haven't I? So I believe that is the end. So